So the overall idea, how come you're not taking notes? The overall idea is for stresses and beams, the total stress at a point is the stress due to tension or compression plus the stress due to the bending moment plus the stress due to the shear force plus the stress due to the torque. This one was really easy. So now we're talking about this one. So stress due to bending moment. And the type of stress is the X normal stress. And the formula for it is negative bending moment Y over I. Where Y is the height relative to the neutral axis. Remember, the neutral axis is the plane where on this plane, when you bend this beam, it stays the same length. So there's no compression and no stretching. Okay, so let's think about how this sign works first of all. So let's think about it in the case of a positive bending moment and a negative bending moment. Okay, and let's think in both cases, well, the neutral axis is the middle. Okay, so the neutral axis is somewhere there. And let's think about a point above and, below. And then same thing over here. Okay, so in this case, this is a positive bending moment. If you started with couples like that at the ends and went in and calculated the internal loads, you get positive bending moment. So this is a positive value of M. And so what happens if you start at the neutral axis and go positive Y? Okay, so we're going up to the red one. Okay, this formula says for that red point, Y is positive, M is positive, I is always positive. We'll talk about what that is. And so in this case, that red dot should be in compression. It should have a negative X normal stress. Okay, you see that? And then think about what's happening here. Think about that being like the inside of the track. This is the short part. And so that makes sense intuitively. Now this one, go to the blue dot. We're still dealing with a positive bending moment. Y is negative. So all of this becomes positive. And that says that the X normal stress is positive. So it's in tension. And that's what you would expect if you bend it this way. Okay. And everything works the same but opposite in the other case. So now we have a negative bending moment. Um, and so m is negative. If you go to the red dot, y is positive, divided by a positive. So sigma xx should be positive. It should be in tension. And that's what happens if you, to the top, if you bend something that way. And if y is negative, then you have negative, negative, negative. Sigma xx should be negative, and the bottom should be in compression. Yes. Well, really the way you do it is you make a cut and calculate the internal loads. Um, so like if I made a cut here, and the only external load we have is this, and then we have our internal loads. It has to be counteracted by a moment like that, and that's a positive bending moment. No, it's not. That would make it spin, but that's the idea. In order to have equilibrium, you have to do it like that, which is a negative value of m. Yes. Yes, because of the way that the couples you have to apply to make it do that. Yep. All right, and so that's where the sign comes from. So the sign makes intuitive sense, and that means just trust the sign. I mean, it's always good to have a picture in your head of what's going on, but signs will take care of themselves. Um, and then the other thing we have to consider is we have to know what the limitations are on the shapes of the beam. So beam restrictions. There are 3 of these. Anyone remember any of them? Yes. Are you remembering or are you reading your notes? Okay. Yes, straight. Or nearly straight. Prismatic. That was the one that's up with. Prismatic. Or nearly. Those nearly things are sort of a nuisance because it gives you like some wiggle room or whatever, but it's just saying the farther you get from these, the less accurate your results are going to be. And then the last one is symmetric. Of the y-axis. So we can do beams with a cross section like this. But we can't do ones like this. Can you believe it? That's bullshit. This one's okay. That's fine because the y-axis is this. Well, it depends how it's, if it's, yeah, right. How it's, it depends how it's oriented relative to the bending moment. But this is the y-axis. So that's the key axis of symmetry. And good luck finding beams like this. All right, so now we need to define neutral axis. and I, which is the area moment of inertia about an axis. And people just call it the moment of inertia. So this, you do need to keep this stuff in mind, or you'll get confused about this versus one that you use in dynamics, which has a lot of similarities, but it measures something different. So the neutral axis. Um, the neutral axis is for a given cross section. It's parallel to the z-axis. And it passes through the cross section's centroid. Um, that's pretty nice, simple fact. So if you're thinking about, okay, there's this sort of theoretical place on a beam where when you bend it, the length is not going to change, you know, it seems like a lot to expect, a lot to hope for. That's just going to line up with where the centroid of the cross section is. And that's what it does. So if you have a shape like this, there's the beam. There's the x-axis. There's the y-axis. There's the z-axis. Just put the origin at the centroid of the cross section. And then the neutral axis is just the z-axis. And remember, that's for a single cross section. And if you draw the neutral axis for every cross section, here's one, and then go back a little bit, and there's the next one, and there's the next one. What you get is a, like sawing this salami in half this way. You get a plane that goes through parallel to the z-axis all the way back. So what does that look like? Not like that. What? That red is a plane that defines all the neutral axes. What? Yes, it's the XZ plane. I don't think I've ever thought of it that way. Yep. Yeah, that's kind of the um, that's where things get really messy with the math. But for us, we're lucky. We're dealing with very small deformations. And so we always assume that things look the same before and after the deformation. And so for us, we don't have to worry about that. But as things get more complicated, as you start dealing with bigger deformations, then yes, that's a serious problem. Any other questions? All right. So that's it for the neutral axis. And the next thing we have to define is the area moment of inertia I about an axis. Um, and the definition is an integral definition because that the word moment is a mathematical thing that is defined by certain types of integrals. And I about an axis A is equal to the integral over the entire cross section of y squared dA where y is, well, let me say this differently. Where the origin is on the axis A. For us, the axis A is going to be the neutral axis. And so we'll put the origin at the center point of the cross section and use this formula. I think I did the same thing in dynamics. I'm just going to do one integral calculation, but really we're just going to use formulas. So let's say that we have a beam and the cross section is this. The neutral axis is the horizontal line that goes through the centroid. So we can call that the origin. Then the z-axis is this way. The y-axis is this way. And the z-axis is our neutral axis. And that's our axis A. And so what we're going to do is, for a single cross section, let's say that the dimensions are, let's call that B and this H. And this is the neutral axis. And to do this integral, I'm going to, okay, look at the integral again. We need to divide this cross-sectional shape up into infinitesimal pieces dA, little infinitesimal areas, okay? And we need to do it in a way that, you know, in order for us to calculate this integral, each one of these dAs has to be made up of all points that are the same distance or have the same value of y. Okay, because otherwise, um, the idea is we're trying to break this up into pieces where we can say, okay, that piece has a y value of this, add that to the next dA, and it has a y value of this. That's sort of always the approach with these kind of integral definitions. Okay, so I'm going to break this up into pieces like this. So this is my piece dA. The width of it is b. The thickness of it is dy. And so the infinitesimal area dA is base times, the height of that little sliver, so dy, birthday. The height, since this has an infinitesimal thickness, this is just our y value here. And so I sub a is the integral from, okay, and why did we define dA like that? Well, since we already have the y's in there, it would be nice to define our infinitesimal area in terms of y, then we can integrate with respect to it. We found this relationship between area and y. So now, plugging the formula, y squared times dA, which now we have written as b dy. And what are our bounds of integration? Because of where the origin is, we could do it from 0 to h over 2, and then, but let's just do it from negative h over 2 to h over 2. And so we can pull out the b, and we have y cubed over 3 evaluated from negative h over 2 to h over 2. And so that's b h cubed. When we cube that 2, it's an 8. So now in the denominator, we have 3 times 8, so 24. And then minus b times, since this is a cubic, that negative comes through, so we have negative h cubed and over 24 for the same reason. And so we come up with a formula b h cubed over, we have just 2 times, 2bh cubed over 24 is bh cubed over 12. Okay, so what does this say intuitively? Notice not all dimensions are created equal for this. The height of the cross section is way more important than the width of the cross section. Okay, where have we seen something like that before? So last time we didn't start doing the calculation, but I did say that, okay, this is the same piece of paper under the same bending load in this configuration and in this configuration, okay? And the cross section is like this is the cross section, or this, okay? If we hold it like this, okay, then we know that it's very easy to bend, right? It should have a very low area moment of inertia. So look at this formula, and what happens when you plug these in this configuration. The base is big, but the height, the thing that you cube, is tiny. And if you cube something tiny, it gets super micro tiny, okay? And so that's why this has no ability to support bending loads like that. But if you take the same material and turn it like this, now the base is tiny, but the thing that you cube is big. And so you get, many, many, many times more resistance to bending in this orientation than in this one. And structures that you make for building, well, not structures, objects that you make to build structures out of, like I-beams, are useful because no matter how you orient them, they have a relatively small amount of material required, but still provide a lot of resistance to bending because you're moving the flanges at the end, you're getting them far away from the center, and the integral formula for the area moment of inertia rewards you for getting stuff far away from the centroid. How many people here have ever taken intro to engineering? Anyone? Did you do the bridge crushing thing? Okay, so you probably either sort of intuitively understood this about resistance to bending, or else you sort of figured it out as you went. You didn't get rewarded much for using your material to make the thing wide. You only had to make it wide enough that you didn't get some kind of weird twisting and then it would break the other way. What you're really rewarded for is making it tall, getting the material separated really far from the centroid vertically. And again, it's not really an issue of, I say tall because we're always thinking of these things bending up or down. It's really the relationship between the shape and the axis of bending. But we're always going to do these problems with the axis of bending being like the z-axis. Okay. There are two really important shapes for us. So let me give you the formulas. The area moment of inertia for simple shapes. The first one is a rectangle. This is the one we just calculated. There's an L in there somewhere. So that's the y-axis, that's the z-axis. We'll say it has a width b and a height h. And if this green is our axis, then I sub a is 1/12 base times height cubed. The second one is a circular cross section. There's y and z. We're dealing with a radius r. And for this, so z is the axis we're talking about. Area moment of inertia about that axis A is 1/4 IR squared. No, IR to the fourth. That would make sense with the units. What are the units of the area moment of inertia? Yeah, meters to the fourth. And then actually we'll use triangles a lot too. I don't have it written down here. We will talk about how to add shapes. So we'll do it only for equilateral triangles though. It doesn't have to be equilateral, just isosceles triangles. And the reason we only care about isosceles triangles is because we're restricted to shapes that have those symmetric cross sections. So you can calculate the area moment of inertia for anything, but you can't use it in this formula unless the shape is symmetric about the y-axis. Are we going to really just go through the pain of calculating this from the integral? We should, right? For a triangle? Okay, I'm not putting this in the notes.